Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. The topic was binary tree and the pattern was serialization or construction. From this pattern we will do the next question, which is flatten binary tree to linked list. So I hope you all are aware with linked list data structure, what it is and how it looks like. And now we'll move to this question. So let's read the problem statement. It says we'll be given the root of the binary tree and we have to flatten the tree into a linked list format such that, how we have to do? We have to move all of its left child towards the right side, okay? And we have to make every node's left side as null after moving left children's towards right side, okay? Now let's read the constraint. It says the minimum number of nodes can be 0 also, and at max 2000, okay, and the node values can go till -100 to +100. Why we read this? Because if we have to do some multiplication and summation, the values might go beyond the integer coverage. So hence we know that up to 10 power 9 the integer can hold the value, so it's totally safe because we don't have to play with the values. Okay, so this is a question which is the first approach which hits our mind, as we have to move all the nodes like this. And if we see this very clearly, first 1, then 2, then 3, then 4, then 5, then 6. 1, then 2, then 3, then 4, then 5, then 6. And if you see this, if you have solved that pre-order, post-order and in-order traversal, then this is nothing but the pre-order traversal. So the very first approach which should hit your mind is, why not to do the, pre-order traversal for this. So if we do pre-order traversal, first we will write root, because what pre-order says? Pre-order says first root, then left, and then right. Correct? So first root means 1. Now we'll go towards left side means 2. Now we'll go towards left side of 2, which is 3. Now root done, left done. Now it's time for right, which is 4. Now root done, left done, which is 2, 3, 4. And now it's time for right side. For right side, the first should be root, which is 5. Okay. Now root done, left, which is null. So we'll not write anything. Now right side, which is 6. So in total, root, left side, right side, right side. So hence this is our what? Pre-order traversal of the tree. And now what we have to do? We have to make like this, right? Remember, you cannot make a node which is 1 and then connect its dot next to 2 and dot next to 3. No. You cannot change the structure of the tree. The structure of the tree still says ki root will be there, its left child will be there, and its right child will be there. Remember, you're not allowed to make a new tree like this. No, you are only allowed to rearrange the same tree to this. You have to rearrange, okay? So first thing, it's very important to save the pre-order traversal of the tree, but instead of saving the values, we have to save the root. Why we have to save the root? First, we'll pick this from the list, okay, or array, like wherever we have stored. Okay, now this, let's say this is a current node, okay, current node, and towards its right side, we have to fix the next. So if this is the ith index, I plus 1th will be what? So we'll say, how we'll say, ki suppose this is our list, right? So we have to say ki list dot get I, which is root, dot right side, we have to fit list dot get I plus 1. Now we can say ki for this one, once right we have 2. Now, but once right we have 2 is okay, but we have something in the left side, right? So we have to make this null. So it's very important ki after connection of this, we have to say ki list dot get I dot left side, we have to make this null. Now we can say ki yes, we are actually moving towards this. So now after one iteration, how the tree will look like? 1, because we have connected 2 as a node, so we will have like this 2, 4 also, and here we have none. Now our task is to move for the next index, which is 2. So for 2's right side, we will fit the next one, which is 3. So 2's right side, we will fix 3. So 2's right side will have 3, and now 2's left side, we will make it null. Correct? Now we'll move to 3. Now 3's right side will have 4. 3's right side will have 4, okay, and 3's left side will be null as it is. Now we'll move to the next. 4's right side will have 5. So we'll connect 4's right side, which is 5, and by default 5 and 6 will also get connected because they are connected, right? Okay, and now 5's left side is null, which is by default it was null also. Now we'll stop here because I plus 1 we have to connect. So if we'll go till this end now, it will say out of index. And one more thing, when we are doing this pre-order traversal, we know na ki for sure the last value which we will write will be a leaf node. Means its left and right will always be null. Then it does not make sense ki go and attach something at the right and something at the left. Okay. Yes. So hence the very basic approach is ki do the pre-order traversal, store all the nodes in the list. Okay. And now one by one start iterating from the ith index, set the right side nodes and reset the left nodes as null, and that's it. Okay. So let me show you the code directly in the editor. So here is the code what we have written. First we'll make the list of tree node type and we'll call the preorder function. Here is the preorder. I hope you all know how to do it. Now one by one we'll run inside this with the index 0 till second last, and we'll make its left child null and right child will set to the next one. So talking about the time complexity, first it will take O of n time complexity for this pre-order traversal and space complexity because we are actually storing all the nodes in the list. Okay, further O of n space complexity as well. And the second O of n time complexity for this because we are running the for loop till the size of the list, and size of list is nothing but the number of nodes. Correct? So total time complexity will be O of 2n, although it is also good, but it's not optimized because we are using like taking extra space complexity, which is O of n by the list and O of log n by the recursive call stack. Okay. So this is a brute force code and you all should be able to do this. Now what will be the optimized approach? That we will see. And the optimized approach is Morris traversal. If you don't know, obviously, if you have never heard about it or learned about it, this will be the first time. So you have to learn it first and then only you can be able to think on this. Okay. By the way, the most genius people can think directly also. Okay. So the approach is very simple. You are here at the root, right? So what is our task? Our task is to shift everything towards right side. Correct? Shift everything towards right side for every node. Here we are starting from the upper node. Okay. There one more solution ki start from the rightmost leaf node and start connecting everything towards top side. Okay, but we are going to do the Morris traversal where we'll start from the top and go till the bottom. Okay, so suppose this tree we don't have, right? Okay, so we'll start from 1. Okay, now what we want to connect left node towards the right side. So it will look like this. Can I say that? But if you will directly write this line of code now, what? Ki root dot right set what is there in root dot left. Then you might lose what was present at root dot right. Correct? So it is very important to save this in some temporary variable. Can we say that? Yes. So tree node type make a temp variable and in that let's save root dot right we will save first. Okay. So root dot right which is 5, 6 we will have in a temporary variable 5, 6, okay, in temporary variable. Okay. Now, as we have connected, but you know na ki we had 2, 3, 4 here also. So after this line of code, this is how our tree will look like. But we have to make the whole left as null, correct? So it is very important to set the root dot left side as null. And now we can say ki yes, this is how our tree looks like. Now, listen it very carefully. Where are we currently present? Let's say current is here. Okay. Now what is our task? This node needs to be connected, but where? At 3 or at 4 to make it right side? At 4. Okay. And where is this 4? Can I say ki if I will start from current dot right side, if I start from 2, keep moving towards the right side until it is present. Why we are doing? Because this is what is expected. This 5 and 6, like whatever was my right side element, we have to connect it towards leftmost right side node. This is what we did now. Like left subtree we connected to right side. Yes. Now this we have to connect it back. But we have two options, either at last like leaf nodes towards left side or right side. But as we have to make it left tilted, so it's very important to connect the 5 to the 4's right side, not left side, not like this 5, 6, no, like this 5, 6, correct? Just we have to connect 5, 6 will get automatically connected. Okay, don't think about all the solutions. As of now we are only cleared with this. Okay, we are only connecting this node so that in the temp variable where we have stored 5, 6 now, when we'll move to the next, obviously in the temp variable we have to store this na 4 and whole instead of only 5, 6. So hence it is very important that whatever you have stored in temp, please connect it back and free this temporary variable. This is the main purpose why we are doing this. Okay, so as we have to connect this temporary but at the rightmost node, so we have to get the rightmost node. Okay, so what we have to do in tree node type rightmost variable, we will call a function, let's say rightmost. Okay, rightmost, and there we have to send what? Here we are, and we want rightmost for this subtree, right? So it's very important to send 2 as node. So we have to send current dot right as node. So what this function rightmost will do? Rightmost will keep traversing towards the root dot right, root dot right, root dot right until the right is present. Once the right side child will be null, will return. What will return? That node. Okay. So let's write the rightmost function now. So in the rightmost function, we will get what? Root. Okay. So until our root is null? No. Until our root's right is null. Until it is not equal to null, we'll keep moving our root towards root dot right side, and once we are coming, like once we are outside this while loop, we will just return, the root. Okay, so now let's see how this will run. 2 we will send, right? So we'll check, does 2 has right child? Yes. So move root to root dot right, which is 4. Now in the while loop again we'll check, does 4 has right child? No. So come outside the while loop and return the 4. So in the rightmost we will have 4. And now we have to connect this temporary towards 4's right side, correct? So rightmost dot right, we have to connect temp. Now this will look like and done. Temporary is like temporary has 5, 6 as of now. But now we are free to override this temporary. Okay. So this is our rightmost function. This will be outside this. Okay. Okay. Now what will happen? For this, we did the entire thing. Okay. Now the next task is, we can say only till current the definition is correct. Like make binary tree to linked list. Now we have to do for 2. And what is 2? Where it is present? Can I say current dot right? So can I say move our current to current dot right? Yes. So move our current to current. So move our current to current dot right. But wait. See here in this case, we'll let you know what I'm trying to say. As of now, we'll move our current to this. Okay, so current will get moved to 2. Now again, we'll go, but where, like as we are moving our current towards right, so it's very important to close this in a while loop also, na? Until our current becomes null, keep doing this, correct? So hence we have to close this in a while loop. While our current is not null, keep doing this. Okay. Now what we'll do? See, current is null? No. Okay. So now what we'll do? Its right side, we'll save this in a temp variable. So now how the temp variable will look like? It will look like 4, 5, and this is how the temp will look like. Okay. Now what we'll do? Now, whatever is there in the left side, we have to connect to right. So now 4, 5, 6 will get removed and 3 will get moved here. Okay. 3 will get moved here. Okay. Now, the left side, we have to make it null. So this will get removed. Done. Now our task is to connect this temp to the rightmost node. Okay. So for 2, we have to send, in the rightmost function, we'll send 3. Okay. Now in the while loop, we'll check, does 3 has right child? No. So means 3 is the rightmost node of its subtree. Correct. So now 3 will get returned. So in 3's right, we have to connect temp. So I can say connect 4, connect 5, connect 6. As of now, I can say it has been done, but we cannot return this because by seeing we can say this, but until we traverse, until we move our current to everything, we cannot say, right? Yes. So now again, we'll move here. Listen it very carefully. Before moving this, we have to move our current to right side, which is 3. Again, we'll check here, is current null? No. So in the temporary, please save the right side, which is 4, 5, 6. Okay, we will save it as of now. That's what we had already saved also, right? Okay. Now make it whatever is at the left side, move it here. Now from the left side, get the rightmost node and make the left null. Don't you think this is not needed because its left was null? So don't you think we should do this much operation only if left is not null? Because if left is already null, how does it make sense to, okay, bring everything which is there in the left side and now make the leftmost side null, and then please bring the, left side's rightmost child? It does not make sense, right? So hence, do this much operation till now, okay? Only if this much operation, only if your left side current dot left is not null. Why? Because if your current is left is null or your current left is not null, anyhow current is going to move towards the right side. So hence this last line, current is equal to current dot right, we have to keep it outside the if case. Okay, so now what will happen? We'll check, does it has left child? No, it is null. Okay, so don't run this much line of code because we'll put this in the if case. Okay, so just move your current at current dot right. So now current will move to 4. Now does 4 has left child? No. Okay, move your current here 5. Does 5 has left child? No. Now move your current to 6. Now 6 has left child? No. So move your current to null. And now we'll see current is null. Yes, come outside. That's it. Very simple. But the time complexity here, as you can see, we have moved to, current has moved to every node. So O of n for sure. But we are calling a rightmost function over here. Can you see this? Yes. And what rightmost is doing, if you remember, first we moved our current at every node. That we can say only total O of n. But inside this also, we moved to this node and we moved to every levels to get our rightmost node. Correct? Why only levels? Because when we called with 2 node, we did not went on the left side. We only went on right side, right side, right side, right side. So only number of levels. So do you think it's O of n into log n? It's exactly O of 2n. How? If you visualize this very carefully visualize this very carefully. When you say this O of n into log n, it means for every node you are saying move to log n side. But do you really think we will need this? I don't think so. So in the worst case, you are moving to the nodes, but only for twice. See, here you move for 1. Now to get the rightmost, you move to 2 and you move to 4. So 2 and 4 you already visited, let's say. And 1 you visited because of current. Now when it get connected like this, so when you moved your current to 2, so again you visited 2 again, correct? Now when you move to 3, when you move to 4, now again you visited 4 again, correct? So 4, 4, 2, 2, 2 times only. So in the worst case, if you'll see in the worst case, every node you will visit at max 2. One time because of the current movement, and other time, in the worst case, other time to get the rightmost node by this function. So O of 2n time complexity. And space complexity, if you see this, we have not used any data structure to save our nodes, or we have not called any DFS function that will further take our O of log n time complexity because of call stack, recursive stack. So hence this is the most optimized code because the space complexity by this code is just O of 1 constant only, right? So that's it. Let's write the code in the editor. So here is the code what we have discussed. First we'll make the current alias for the root, and now we'll close this in a while loop instead of calling the DFS function because it will take further O of log n space complexity because of the recursive call stacks, right? So we will check if our current dot left is not null, because we'll do all this operation of storing our right side in the temp variable and moving our copy of left side towards right side and all those movements only when at least left is present. If left is null, then it won't make any sense. So hence just move your current towards the right side. If it is not null, save your right side in the temporary variable, move your left side towards the right side. Now make left as null. Now to connect your temporary back to the right side, get the rightmost node from the current dot right side. Now this function is to get the right side, like rightmost node. That will take further O of log n, right? In the worst case, yes. But we just saw it seems like it's n log n. But in the worst case, we just saw at every node we are going for just 2 times. Okay, not log n times. Yeah. So that's it. We don't need to return anything, because we were expected to change the structure of the tree, and that's why we have put it inside the construction or serialization pattern. So this is the code in Java. This is the most optimized code. You can say space optimized code. So here is the code in C++ with a similar approach if you are from C++ background, and here is the code in Python if you are from Python background. So that's it. I hope you understood. If yes, please make sure to hit the like button, and please do comment ki yes you understood, or if you feel you get confused somewhere, that too also let us know. Until then, you can go in the sheet and mark the next question as done. And congrats. for the next question submission as well. That's it for this video. If you have any doubt, you can definitely reach out to me through social medias. I'll attach the sheet link and my social media links in the description. And let's meet in another video with some more interesting questions, topics, and patterns. So then keep learning. Take care of yourself. I'm your